So, Chapter 3 review. So we're dealing with whole number models and algorithms. And the first thing we'll take a look at is division. So we had 4 different division models. One was groups in, 2 set partition, 3 repeated subtraction. There's no special order here. And 4 is the missing factor. And so let's just look at the difference between groups in versus repeated set partition. So let's suppose, how about 10 divided by 5. So if I state that division means groups in, then kind of a generic story problem would be how many groups of 5 are in 10. That's pretty lame, but yeah, that works. So this is like as generic as I can get, just because I'm trying to get the main point across, because I want to compare this to the set partition. So what's that going to look like? Well, I'm looking for groups of 5 in 10, right? So that means I need to see the 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then I want to collect them into groups of 5. And so, well, 1, 2, 3, 4, 5. So here's one group of 5, right? And then this over here would be another group of 5. So then I can answer the question. There are 2 groups of 5 in 10. So that's the groups in. So now let's do it again with the set partition. Same problem, same numbers. So now I'm going to say, well, division could also mean a set partition. So a partition is something that splits things up. It divides something. So here, what is the question that's being asked? Well, it's kind of 2 parts. If you split 10 into 5 groups, how many are in each group? So this is a kind of a common problem if you're distributing stuff to people. Like I've got a whole bunch of chocolates and I want to give them out to my friends. So I have 20 chocolates and I have 5 friends. How much does each friend get? That's a set partition problem. Each friend is the set. I need to know how many things go in each set. It's completely backwards what if I have here. Here I know how many are in each set, but I don't know how many sets I have yet. Okay, so in this case, I have to make my 5 groups. And then start counting out the 10 things till they're evenly distributed. And you have to do that one at a time. So then I say, okay, you get 1, there's 1, 2, 3, 4, 5. I still have some more, so I keep giving them out. 6, 7, 8, 9, I had enough, 10. Oh, there's 2 in each group. Notice, totally different physical scenario. Okay, so the groups in, we know how big the group is, but we don't know how many groups. Set partition, we know how many groups, but we don't know how many are inside yet. The answer to the question solves the division problem. Yes, yeah, because you got to demonstrate it. Yeah, so you got to first say, what does division mean? Then based on that, that model leads to a question. Then answer the question. Absolutely. This will be on the test. Yeah. And we have 2 other models too, right? So let's might as well hit those while we're at it. Repeated subtraction. Okay. So now I'm saying division means repeated subtraction. So I have to then take my situation. So the question here would be, ooh, did it crash or I just hit a weird button? I clearly hit a weird button. There we go. How many times can I take 2 from 10? Considering subtraction means take away. And so here I could just say, well, 10 minus 2 is 8. So there's 1. 8 minus 2 is 6. There's 2. 6 minus 2 is 4. There's 3 times. 4 minus 2 is 2. 4 times. And 2 minus 2 is 0. And I'm done with my takeaway. And so I get answer is 5. And then the 4th model basically comes from the idea of fact families. So I could say division means a missing factor. Does anybody remember the alternative name I had for this model? That's right. Division means what do I multiply by? So I called it the what do I multiply by model. So I have 10 divided by 2 equals what? So I write it up like that. And then you read it backwards as a multiplication problem. So reading it backwards would be what times 2 is 10. And so then we think, okay, what can I multiply by 2 to get 10? 2 times 2 is 4, 3 times 2 is 6, and eventually, oh yeah, 5 times 2 is 10. And so this relies on me knowing some multiplication facts. Okay. I mentioned this relies on fact families. So the fact family here would be, we should know 5 times 2 is 10. What's another fact that goes with that? 10 divided by 2 is 5. What's another fact that goes in here? 2 times 5 is 10. And what's the 4th fact? 10 divided by 5 is 2. Yeah. And you'll see this in a lot of workbooks, textbooks these days. Fact families are pretty popular. We want to get them across what mathematical property is that right there? You remember what that one's called? Starts with a C. Commutative. Yeah, it's the commutative property. We'll go over the properties too in a minute. So for any model, I have to look at the problem and say, okay, which model am I going to use? Division means this, subtraction means that. Once I establish which one I'm going for, then I have to say, okay, what question does this model lead me to? And then how can I illustrate that question to come up with an answer? So that's what the models are all about, some physical situation. Questions? Okay. And so usually I'll say something like, given a problem like 10 divided by 2, can you show me what the answer is with 2 different models? And you pick whichever 2 you like. It's up to you. I like seeing what you guys pick. All right, since we brought up the commutative property here, let's go over some properties. My hope is you read about these in the book. Remember, you're supposed to read the book. I cover most of the stuff in it, but not everything. So properties for whole number operations. Popular properties are commutative. What's the other one that usually goes along with commutative? Associative, yeah. Anybody know any other properties? Distributive is one. Let's see, blank, blank. Let's put it here. There's a couple of other more basic than distributive that are pretty popular. Identity, yeah, that's a good one. And that's another one, yeah. 0 as a special property. So does 1. And then the other one is inverse. Oh, and there's another one, closure. Right. Okay, so those are most of the properties there. So what we're going to do is we're going to make a table and take a look at how these properties apply to the different operations, of which we have 4 or 6, depending on how you count. I'm going to worry about the main 4. So addition. So commutative, think about the idea of commute. Anybody commute from home to school? Nobody lives at school right here, at least not on this campus. And then you commute from school to home. So to commute means you have to move, agreed? And that's what the commutative property is all about. Addition is commutative, meaning you can move them and it doesn't matter. So off to the side here, a little illustration. To commute means to move. 2 plus 3 versus 3 plus 2, they both lead to 5, right? You can move the numbers and it doesn't change the result. Does that work with subtraction? 2 minus 3 versus 3 minus 2. That's a problem, right? -1 versus 1. So we cannot move subtraction elements around. Doesn't work. By the way, there's a popular word that comes up with subtraction called the difference. Right? We've used that word before. Did you know difference has a special meaning that's slightly different than subtract? So if I said, find the difference in our ages, right? How old are you? 20, I'm 46. Oh shit, no, I just turned 47. Yeah, no, I'm 47 now. So we would subtract, and so let's see, then the difference is what, -27? That make any sense? No, what would we say the difference is? Yeah, so when we do the difference, we subtract in such a way that the answer is always positive, right? Whereas sometimes when we subtract, we get a negative answer. So the difference is always looking for that guy over there. The difference wants a positive answer. Just little terminology I didn't mention before. I'm not sure if it's clearly spelled out in the book, but that's what the word difference means, okay? So a lot of times when people are talking about a difference, in algebra books, they'll put absolute value around the two numbers to make sure we always get a positive answer. But usually difference means take the larger, subtract the smaller. But subtraction doesn't have to mean that. But that's how kids start off thinking about it. Okay? In the first few grades, you will never ever do 2 minus 3. Well, some kids ask about it. Will it come up? It will come up at some point, right? And you got to figure out how to deal with it. So we'll talk about that next. All right, so commutative, back a slide. So addition is commutative, but subtraction is not. Multiplication. What do you think? Commutative? Yeah, and what is there anything multiplication has on its side that helps us with that? Let's see, new page. To commute 2 times 3 versus 3 times 2. Because let's see, multiplication, what's a model for multiplication, somebody? Come on, think, multiplication model. Oh, somebody, come on. Multiplication models, we have a few. There's at least 3. Groups of, yeah, that's 2 groups of 3, right? Okay, so here's a group of 3, here's another group of 3, right? Versus 3 groups of 2. Here's a group of 2, here's a group of 2, here's a group of 2. Are they the same situation? They are different. So model-wise, they're not the same. But the answer's the same. They're both 6 in the end. So when we talk about commutative, that switching the order leads to the same answer. The models may lead to 2 totally different situations. That's okay. But the answer's the same. How about division? Like 4 divided by 2 versus 2 divided by 4. Yeah, 4 divided by 2, that's 2. 2 divided by 4 is not even a whole number. If we want to start talking about switching division, then we have to get into what are called the rational numbers or the fractions. When we want to start talking about flipping subtraction, what set of numbers do we end up talking about? That have the negatives and the positives. Starts with an I. Integers, yeah, integers. We're going to talk about them next. All right, so let's go back to our table. So what do we have? Division is a big no. Is that all the operations we can do with whole numbers? Add, subtract, multiply, and divide? We missed one. What is it? So let's see. We started with addition, right? That's the most basic. You just put stuff together and count it. That leads to subtraction because you put stuff together, you want to take stuff apart. If we repeatedly add, we get multiplication, right? What happens if we repeatedly multiply? We get powers or exponents. Yeah, we didn't talk about that. Let's talk about that a little bit. Exponents. Are exponents commutative? Interesting. Let's take a look. Let's see, I'm running out of room. Need more room. Commute. Let's see, like 2 to the 3rd power versus 3 to the 2nd power. So exponents mean repeated multiplication. So that would mean 2 times 2 times 2. That's 8, yeah. Versus this guy over here, which is just 3 times 3, which is 9. And so, no, they don't work that way. We'll come back to powers in a minute. All right, nope. Associative. What's the root of associative? Associate. Hi, it was great to see you at that party the other night. Good job out there. It's good to see you too. Hi. Hi, it's good to see you. Sorry, my hands are cold. Sorry. I'm just kidding. I'll shake your hand next time. So associate means to, go talk to somebody, right? To be with somebody. So it's different than commutative, although I did have to walk around and talk to you. You associate with things that are near you, okay? And so new page, actually, let's go right here. So if we associate, there we go. With two things, they have to associate. They're stuck together. However, if we throw in a fourth thing, or third thing, sorry, number 4, we could choose to associate those guys first. However, we could also choose to associate those guys first. So I'm not moving anything. I'm just changing the association order. Okay, and associate just means check out what's next to you. So the black version says 2 plus 3, provided we know the order of operations, right? Parentheses first. 2 plus 3 is 5. 5 plus 4 is 9. The blue version changes the order of operations. That's why parentheses are first. 3 plus 4 is 7. Plus 2 is 9. Oops, 7 plus 2 is 9. So if we can change the association and still get the same answer, then we say this operation has the associative property. So addition, does it matter how we group stuff? The answer is no, because addition is grouping, right? It's grouping and counting. So this works out great. Addition says, hey, that's what I do best. I'm a grouper. And so we've got a yes here. Now, subtraction fails commutative, so it's like out of luck forever. There's no properties that work well with subtraction. So we'll pretty quickly see subtraction is not associative. Right? You do a couple examples, it all goes to hell. Let's try one just for the heck of it. I better start with a bigger number. How about 12 minus 2 minus 1? The standard order of operations is no different than putting parentheses there. If we work left to right, 12 minus 2 is 10. 10 minus 1 is 9. However, if I try to reassociate like that, 2 minus 1 is 1, and then I got to deal with 12 minus 1, which definitely ain't 9. So I have a problem. And when we talk about integers more, we'll kind of get to the root of what's wrong there, but it doesn't work. So no unassociative. I think red X's might be more appropriate, make them stand out. Multiplication. Can we change the association of multiplication? Let's switch to blue. So 2 times 3 times 4. So natural order of operations is to do that, reading it from left to right. That would be what, 6 times 4? On a good day, that's 24. What about if we switch it? 2 times 3 times 4. So to associate, you do not change the physical order. You're not commuting. You're just regrouping 3 times 4, 12. 2 times 12, hey, that's still 24. Anybody have a thought about why multiplication worked well with associating? Changing the association? It comes down to what does multiplication mean? Okay, groups of, what's another model? Repeated addition, yeah. In addition, yeah. So because addition works, and multiplication is repeated addition, it tends to keep those groups together well. Division probably isn't going to work, right? Because division is repeated subtraction, so division is probably going to be out of luck, right? So if we check division while we're here, let's try 12 divided by 2 divided by 2, for example. Natural order of operations is this one, which gives me 6 divided by 2, which is 3. Versus 12 divided by parentheses 2 divided by 2. Uh-oh, 2 divided by 2 is 1, and dividing by 1 is kind of boring. Fails. The rough thing about the associative property is you can show something fails with a single example, but you're really not showing something's true with a single example. It's just evidence, but it doesn't establish it as true. We need a whole line of thought that goes with it. We're not going to worry about that right now. Okay, so let's see. Multiplication was a success. Division was a failure. Exponents. Well, on one hand, since exponents are based on multiplication, I might think, hey, we got a chance. However, how did exponents fare with commutativity? Failed. So I'm thinking it's not going to pass the associative test. So something like 2 to the second to the third power. Ooh, power to a power to a power. This is where things get interesting. First, we put the parentheses there versus putting them here. You give that a shot, see what you get, and we'll compare notes. I think the left one's 64. And we get that? How about the one on the right? Ooh, 2 to the 8th, that's rough. Let's see. 2, 4, 8, 16, 32, 64, 128. That's 8 fingers, I think. No, that was 7. 256. Anybody get 256 on that one? You get that? Okay. That's quite a bit different. Yeah, I would say not associative, right? And the not commutative gave us a hint, but again, commutativity is very different from associativity. Totally different physical traits. And in some sense, these are like properties of chemical compounds. Why do these chemicals have that compound? Well, that property. Well, in some sense, it's their essence. Okay. Often we can find physical reasons that it happens. Sometimes those reasons elude us. So let's see, we just failed right here. Okay, identity. Identity is a number that doesn't change things with the operation. Okay, so is there a number we can throw into an addition that doesn't change a number? 0, yeah. So identities. So 2 plus 0 is 2. 0 allowed 2 to keep its identity. Also, 0 plus 2 is 2. Doesn't matter how I apply the identity. Okay, so this together means that 0 is called the additive identity. Is there a subtractive identity? Answer's no. Although 2 minus 0 is still 2, the 0 minus 2 does not lead us in a good direction. So the identity applies to addition. What is the identity? It is 0. Additive identity is just another word or another phrase for 0. So additive identity is 0. There is no subtractive identity. Is there a multiplicative identity? 1. Yeah, so multiplicative identity is a fancy word for 1. Identity. There we go. Will you likely come across these phrases in your textbooks? Unfortunately, yes. It's good to know, but I don't know if school kids need to know that 1 is the additive identity. That's debatable. So let's see, multiplication, and let's change some colors here. You would be better off, how about blue? 1 is the multiplicative identity. Do you think division is going to have an identity? The answer is no, it doesn't, because we can't reverse it. Is there an exponent identity? Kind of like the division and subtraction thing. The answer is no, but almost. 2 to the first power is 2. Just write the base and there's nothing else to do. But I can't reverse it. Like 1 to the second power, that's still 1. So we really can't go there with exponents. Inverse. What does inverse usually mean? Yeah, so opposite. Now we're getting a little ahead of where we're at, but we need to talk about it a little bit. Inverses. So an inverse is something that leads to the identity. Okay, so there's inverse numbers and there's inverse operators. So for example, 2 plus what equals the additive identity 0? -2? Yeah, so with whole numbers, we're stuck. We have to branch into a different set of numbers. The only answer we can put in there, come on, there we go, is to say, well, -2 is the number I want in there. Okay. So -2 is the additive inverse of 2. So what's another word that we have for additive inverse? Danielle, I'm losing you there. Try sitting up straight, putting your feet down. It'll help. What is it? No, that's not subtract. We're not subtracting here. I am adding here. Very important. Starts with an O. Opposite. Yeah, additive inverse is the opposite of the number. The opposite of 2 is -2. Yeah, so additive inverse, we usually say opposite. Opposite, unfortunately, we use a lot of different ways in math. Like, what's the opposite of addition? Yeah, but we're definitely adding here. I'm not subtracting at the moment. Okay, so we in math, most things we're pretty precise about, but there's some words that get used and bounced around in different ways, and so we got to be careful. Kids will find some confusion about that later. So additive inverse. However, what if I ask the question 2 times what is equal to the multiplicative inverse? What's the multiplicative inverse? Or identity, sorry, 1. 1's the multiplicative identity, right? What could you multiply by 2 to get 1? 0.5 or 1/2, yeah. 1/2, 0.5. By the way, 0.5 is slang. Like ain't is slang. What's the proper way to read that? Yes, nice job. Yeah, the proper way to read this is 5/10. Calling it 0.5 is slang. You're missing out on the place value. That would be like calling 50 0. Doesn't that sound weird when I say that? But somehow we're all comfortable saying 0.5. Do I say it all the time? I'm guilty, yes. So 1/2. And again, we have to leave whole numbers to start talking about inverses. So I could say 1/2 is the multiplicative inverse of 2. Anybody happen to know an alternate word for multiplicative inverse? Kind of like opposite is the alternate, a different word for additive inverse. What's the relationship between 2 and 1/2 or 1/2 and 2? Want a big hint? Starts with R. E. C. Reciprocal. There we go. We got a winner. Reciprocal. So reciprocal is the multiplicative inverse. It's what we multiply by to get the identity of 1. I apologize. I saved most of the boring stuff for today. Definitions, definitions, definitions. Oh, what fun. How many people read these definitions? Anybody? No? It's a good thing we're going over them then. All right. So going back. Oh, there we go. That's what I want. So as far as inverse goes, for whole numbers, there is no additive inverse. Definitely nothing for subtraction, multiplication, division, or exponents. We have to broaden our horizons to bring in other numbers. So wanting that additive inverse means I have to start looking at other numbers. Well, what other numbers do I need? I need the integers. Whole numbers are not sufficient. That's what chapter 5 is about, and I want to jump into that next today. Multiplication, I need numbers that look like that. Those aren't whole numbers. Those are usually called the rational numbers. That's like chapter 6. Unfortunately, we don't get that till next term, and I heard I'm losing a bunch of you before then. I'm so sad. I'm serious, not sarcastic. You're all fun, good workers. Okay, so in order to get those inverses, we have to branch out into other kinds of numbers. And so this is kind of interesting. When people discovered numbers, like they learned to count, they realized, oh, there's more to this counting. We need negative numbers. We need fractions. Was that enough? Were we satisfied at negative numbers and fractions? The answer is no. There are numbers that aren't negative numbers, and they're not fractions, and they're very important. We'll get to those later too. There's even multidimensional numbers. You guys know that? What the heck is a multidimensional number? It's hard to wrap my mind around. It blows my mind sometimes. Here's another weird kind of number. What does infinity mean? speaking of other kinds of numbers. All the numbers? Well, sort of. So there's this hotel called Hotel Infinity. And this guy's driving down the road and he really needs someplace to stay. And so he says, hey, Hotel Infinity, they got to have a room there, right? Infinitely many rooms. So he pulls up and he says, I'd like a room. And the bus boy at the front, and what are they called? Bellhops? Bellhop says, I'm sorry, we're full. What do you mean you're full? This is Hotel Infinity. So all our rooms are full. And the manager's just like shaking his head. Oh, what an idiot. So he goes over to the kid, says, excuse me, just I'll take care of this. So he says, all right, I will get you a room, it'll just be a minute. And he goes over to the bellhop. He says, get the elder bellhops. You can imagine they have quite a few bellhops at Hotel Infinity, and have each person move to the next room up. So person in room 1 goes to room 2, 2 goes to room 3, 3 goes to room 4, and they can just keep doing that all the way down the line. Now there's an open room. No problem. The bellhop's like, wow, I learned something. This is so exciting. So he's all happy and thinking he can deal with anything now, and up pulls a bus. Guess what it says on the side of the bus? Bus Infinity, it does. And so the tour guy gets off the bus and he says, we need rooms for infinitely many guests. And the bellhop's like, oh my gosh, I can handle like 1 or 2, but I'm sorry, I can't handle infinitely many, we're full. The manager again shakes his head. What are you thinking? So 1, 2, 3, 4, 5. We have rooms going down forever, right? Forever. So infinity has something to do with forever. And the manager again sneaks in and he says, okay, we're going to fix this. Get your people off the bus. We'll find rooms for them. And he tells the bellhop to tell the other bellhops to get each person and have them move to the double of the room that they're in now. Will every single person in a room have a new room to go to? Yeah, there's always a double of the room they're in. Now they might have to walk quite far to get there, but we can get them there. What does that free up though? Now this brings up a mind-boggling thing which people thought about a long time ago. How many whole numbers are there? Well, there's infinitely many, aren't there? Okay. How many even numbers are there? There's also infinitely many, but doesn't it seem like there should be twice as many whole numbers as there are even numbers? However, we can match every single whole number with every single even number and never run out of matches and never have anything left over. Danielle wants to go back to bed.
First off, why would we just put the new people on the next room? Yeah.
Well, they're full. All the other rooms are full. So what I'm getting at here is a couple of things about infinity. What does infinity really mean? We use the word, right? Well, that's part of what it means. Okay, Courtney said it means all of the numbers. Well, all of which numbers? The whole numbers? And then now we haven't even dealt with the fact that there's opposites of all these whole numbers, like -1, -2, -3. So there's infinitely many of those too. And then even better, how many fractions live between like 1 and 2? Oh my gosh, there's infinitely many fractions between 1 and 2. So we use the word infinity to mean many different things in math. Infinity means go this way forever. It means there's a pattern to counting these, and I can't count them all, but I can keep going. I can always tell you the next one. I cannot tell you the last one. Right? Give me a fraction that's really close to 2. 1.99999999999. Could you get closer than that? Sure, throw another 9 on there. You just got closer, right? And that's crazy ideas. Infinity is a weird idea, and it takes some time to get used to it. And there's all these strange things about it. And it turns out there's different levels of infinity. It turns out there really are as many even numbers as there are whole numbers. At some glance, it looks like there should be twice as many whole numbers, but really there aren't. There's the same level of infinity numbers. And as far as fractions go, even though there's a ton of fractions in here and in there and in there and in there, there's just as many fractions as there are whole numbers. And there's really weird ways to prove it. But did you know there's numbers that aren't fractions? Can anybody give me an example of a number that is not a fraction? Well, 1/2 is a fraction, right? 3/4 is a fraction. Comma. 21/7 is a fraction. Actually, let's go 22/7. That's more exciting. It is. Whip out your calculator. What's 22/7? You'll see. Let's see. Google calculator. It's what? Not quite, but it's close. 22/7. Yeah, it was a popular. People thought that might have been pi. But if I ask Google, what is pi minus 22/7? Google says, there's a difference. They're not quite the same. They got a couple decimal places in common though, right? So it turns out pi is an example of a number that can never be written as a fraction. Exactly. Anybody know any others? Square root of 2, because it's not a perfect square, can never be written as a fraction. There's a way to prove that. We'll talk about that next term. And it turns out there's a slightly different level of infinity that talks about the numbers like pi and square root of 2 than fractions and whole numbers. The complexity is greater. They're both infinite, but we can show that there's a higher level of infinity for the other group of numbers. It's really weird. So it turns out, and there's still a lot of stuff we don't know. Even about whole numbers, there's still people studying things and getting PhD in just whole numbers. Just kind of crazy. Like for years, your credit card transactions were secure because of whole numbers. And we'll get to that in chapter 5. All right, let's get back to our table here. Digression. All right, so we can't do inverses yet because we don't have enough numbers to do so. Let's see, where does 0 come in significantly? Where is 0 important? Addition, right? We have the 0 property for addition. That's the additive identity. Subtraction's kind of useful there in one direction, but not the other. What about multiplication? Anything interesting happen with 0 and multiplication? Yeah, it's always 0, so this is kind of weird. We always get 0 there. Let's take a look at that. Let's see, this way, new page, 0. So let's see, what is 0 times 1? 0. And 0 times 2? 0. And 0 times 3? Okay, this is getting kind of boring, right? But these are part of fact families, right? So what's some other families in this like this fact right here? Has other pieces in its family? What would it be? How about 1 times 0 is 0? What else? Division facts related to that? Let's see, 0 divided by 0 is 1? Uh-oh, because if that's true, like over here, this is 2 times 0 equals 0. And if I read it backwards, I get 0 divided by 0 is 2. Ooh. Ah, well, this one says it's 1. This one says it's 2. Let's see. Well, I remember this rule in algebra. If you take a number and divide it by itself, what do you get? 1? Right? Shouldn't 0 divided by 0 be 1 then? No? Daniel says no. I did? I thought I said 2 divided by 0 was undefined. 0 can't be on the bottom? Why not? I can't take 2 and split it into no groups. That is true, but could I take 0 and split it into 0 groups? I think I can do that once and get away with it. Or maybe twice. Or maybe I could do it 10 times. Well, undefined means there's no possible solution. So if I look at the what do I multiply by model here, this would say, what would I multiply by 0 to get 2? I know. Good. It's an error. So question, what would I multiply by 0 to get 2? Nothing. There's nothing. There's no possible choice there. Nobody has yet defined a number that will work. There is none. That's why it's called undefined. 2 divided by 0. 0 divided by 0 is different. I know, but it's still different. So check this out. Check this out. I get another new page. What is 0 divided by 3? Yeah, I have no money. I want to share it with my 3 friends. How much do each of them get? They get nothing. I can totally answer that. What's 0 divided by 2? 0. What's 0 divided by 1? What's 0 divided by 0? Oh, well, this pattern says maybe it should be 0. Are you confused? Good. It's different than 2 divided by 0. Because I do have possible solutions. Don't I have a rule that says 0 divided by some number is 0? 0 divided by 2, 0 divided by 3. I also have another rule that says a number divided by itself is 1. So this rule says, hey, 0 divided by 0 should be 0. But this rule says 0 divided by 0 should be 1, shouldn't it? Which is the better rule? You like the 1 better? I did yesterday, but today I like the 0. Well, does anybody remember what the division algorithm is? Sometimes it's called the definition of division. What does A divided by B mean by definition? Yeah, so what the definition is, there is a number Q and another number R such that B times Q plus R equals A. And there's some conditions on this. Anybody remember any of the conditions? Yeah, R has to be greater than or equal to 0, but less than B. Okay, and there's another condition on this. Yeah, they don't have to be different. They could be the same, but they have to be unique, meaning there can't be more than one choice for Q. Q and R are unique. So I can totally satisfy this part of the definition of division for 0 divided by 0, but I fail this last part. I can't do it uniquely. Okay, so here's what it breaks down to. There are 3 cases with 0, and they are fundamentally different, just like the set partition model is different than the groups in model for division. So let's take some number A, and A has to be greater than 0. If you take A divided by 0, you will always get 0. That's case 1. Oh shit, that's upside down. Sorry. Switch that. Take 0 divided by a. There we go. So 0 divided by 2. I have no money. I want to share it with 2 friends. They each get nothing. That totally works. Case 2. A divided by 0. This fails because there's no possible quotient, right? When we look back at the definition. So it's called undefined. Oops, wrong order. Zero divided by 0, however, is a whole different animal. Oops, why did I do that? 8? No, 0. Because there are many possible quotients here, all with the same remainder. The remainder is always 0. But there's too many quotients, and the definition says it can only be 1. So this is called indeterminate. Indeterminate. There are rules that lead to a possible quotient, but there's no way to determine which is the best rule. There's this rule, there's that rule. They both work. We can only have one. Therefore, we have no answer. Okay, so this one has no answer for 3 has no answer for a different reason 2 has no answer. There are possible solutions. We just can't pick the best one. Okay. Do calculators differentiate the error? No, they just say easy. If somebody puts 0 in the denominator, throw error on the screen. Okay. I wonder what Google would say. Or what's Siri? Doesn't Siri have smart butt answers for some things? Let's see. 1 divided by 0. Division by 0. Google doesn't even bring that into the calculator. How about 0 divided by 0? Doesn't talk about that either. Let's do 0 divided by 2. That gives me the calculator. Can I divide that by 0? Error. That's it. How about 2 divided by 0? Infinity. What gave me a different answer? Holy crap. Why would it give me infinity for 2 divided by 0? That is a discussion for another day. I digressed enough already about infinity. Wow, 0 is related to infinity. Everything, nothing. Oh, that kind of makes sense, doesn't it? What's the opposite of everything? Yeah. Huh. Okay, that's part of the reason. There's more to it. All right, let's see. I had a couple other things I wanted to talk about with you all. Models versus algorithms, 0. Oh no, that's it. Do you guys have any other things you wanted to go over? Yes. So let's go back. Where's our fancy table? Right here. Okay. So 0 is important with addition because it's the additive identity. 0 is important with multiplication because it's special. The answer is always 0. So it's just called the 0 property of multiplication. And it's a property. It's different than the 0 property of addition. Nothing happens. 0 property of multiplication, it's always 0. In division, weird stuff happens depending on where 0 ends up. Okay. Does 0 have any interesting property with exponents? Yeah, let's take a look at that for a minute and see if we can make some sense of that one. So exponents. There's 2 things that come up when people are working with exponents that puzzle them. One is that some number to the power 1 is itself. Why? Okay. The other is that a number to the power 0 is 1. Why? So let's address those. So let's get down to what we think exponents mean. So what I'd like you to do is write down what you believe exponent means and include an example. So exponent means blah, blah, blah. Give me an example to go with it. Multiply, can't spell. Okay, I wrote 2 definitions up there. I don't have any examples to go with them yet. That's next. An exponent tells you how many times to multiply the base. An exponent tells you how many times to write the base, then multiply. Are those the same definition or are they different?
Like if you had like 2 times 4, so it should be 2 times 2 is one of them. It takes the base twice to write the first one.
2 to the 4th, you mean?
Yeah.
Okay, so if I go by my first definition, it tells me how many times to multiply the base. Okay, so 2 times 2, there's one multiplication. There's a second multiplication. Here's a third multiplication, and here's my 4th multiplication. Is that 2 to the 4th? No, oh crap. This is the way most people commonly state what it means to be an exponent. I know what you meant, but that's not what it means. Do I say that sometimes? Absolutely. Why? Because my teacher said it to me over and over and over again. But we really got to be careful. It's not how many times you multiply. There is a way to fix that. It's how many times you write the base. So the correct definition for an exponent is how many times you write the base, then you multiply. So that is 2 to the 4th. So his definition B is the correct one. And it gets misworded all the time in books. We know what they meant because we're the teachers and we've done it before, right? But we want to be careful. Other things to double check here. The 2 is known as the base. The 4 is known as the exponent. What does the word power mean then? We use the word power a lot. Would it be the exponent or would it be the answer? Is 16 a power of 2? Have you ever heard somebody state that? Someone say something that way? No? Okay, let's see. Let's go to the internet and ask. Powers of 2. Ooh, I can even get a list of them. Interesting. Oh my, there's a whole bunch of powers of 2. So it turns out the word power we use in a couple of different ways. It's one of those words, what was another word we used earlier? Opposite, we use it in different ways in math. Power we use different ways. Sometimes people use the word power synonymously with exponent. Other times power refers to the answer. So power, depending on where you read it, could be that number right there, could be that number right there. So we're a little shaky about the way we use the word power. Exponent, however, is that little number up top. It does tell you how many times to write the base, is what it tells you. Now, if I word it that way, version B, that does solve one problem. What does 2 to the first mean? How many times do I write the base? Once. Oh, but I don't get to multiply. Darn it. You want to know some weird trick some people do to satisfy that? Whenever you have something to a power, like 2 to the 4th, you always write a 1 first, and then start going times 2, times 2, times 2, times 2. Then I satisfy two things. How many times do I get to multiply? 4 times. Oh, I didn't before. How many times did I write the base? 4 times. Oh, now I'm consistent in both places. What if I put a 1 here? Do I actually get to multiply? Ah, then I get to multiply too, so it does satisfy both parts of the thing. Would it be suddenly weird for you to start doing that? Have you ever seen that in a book? I haven't. I've seen teachers do that. Is it wrong? Absolutely not. Nothing wrong with it. All right. So 2 to the first power, write the base, and then you're done. Let's look at a pattern. Let's see, 2 to the second power, that's 2 times 2 or 4, right? 2 to the third power, multiply by 2 again, what's that, 8? We now know that 2 to the first is 1, right? And there's a pattern to this list. There's 2 patterns. Can someone describe one of the patterns to me? There's 2 patterns in what I've written here. There we go. Yeah, going up, the answer is doubling each time, right? Or couldn't I state that backwards? I'm dividing by 2 when I head down through the answers here. Right? What's the other pattern going on here? There's a second pattern. Oh, shit. Oh, shoot. Oh, I just recorded that. Darn it. It's 2. I don't know why I wrote that. I said write the base once, and I wrote a 1. It's hard talking and writing at the same time. Have you guys done much lecturing on the board yet? First few times are terrifying, I thought. Especially if there's like a teacher and a principal sitting in back. My first student teaching, the principal came to visit. I don't know. It was very frightening. I did survive it, yes. But I remember I started doing my thing and I looked back and they're smiling and nodding and I went totally blank. Like, what am I gonna do next? Nothing. And it felt like that moment went on for like 5 minutes. It was probably only like 2 seconds, but it felt like I was standing there staring at them thinking, there's the door. I think I'm just gonna leave now. But somehow I got my stuff together and finished. It was scary. Anyway, okay, sorry about that. So 4 divided by 2 is 2, right? So that's one pattern. Divide by 2 each time. What's the other pattern? Going up, multiplying by 2. There's still one more pattern up here. The powers, yeah, these exponents, if you go down, are dropping by 1 each time. If you go up, they're increasing by 1, right? So what's the next obvious power? 2 to the 0. And if I divide this by 2, what do I get? I get a 1. So that's one way to explain it with a pattern. Okay. You can also keep going. What's the next obvious power coming down? 2 to the negative 1. And what happens if I divide by 2 here? Well, I get 1/2. So this tells me that 2 to the negative 1 should be 1/2. And it turns out that's a rule in powers. If you have a negative exponent, you flip your base. You take the reciprocal. Remember seeing that before? Yeah. So sometimes patterns can be really powerful in trying to explain stuff. Okay, I think I've exhausted exponents for the moment. I was going to start talking about integers, but since we had so much fun talking about that stuff, I think I'm going to stop there. And let you guys finish your, what do you call it, activities. Do anybody have any outstanding activities? Outstanding.